All right, welcome back to part 2 of our cliffhanger from the last video. Right. Obviously, we said that there was an issue with what we did with the moment of inertia calculations for the simple shapes, and in particular when we have centroidal axes that don't line up with the others. And for that, we need a more powerful equation called the Parallel.Axis theorem. All right. Now, just to kind of recap what we had happening here, let's take a look at the problem that we were defining in the last video. Okay, we were dealing with this T-beam that was 6 inches wide on the flange, 3 inches tall for the flange. It was 4 inches up from the bottom, and then the web of this thing was 2 inches, and it was centered here. It's 2 inches, 2 inches, and 2 inches. Okay, we called this as my origin. That was 0, 0, and we went and we found that the centroid location for X bar and Y bar, we found those as already, and we'll recap those when we start pulling those in. Okay, so all we're going to do is we're going to start drawing some sketches that are similar to these guys when we do our moment of inertia calculations. All right, so here's kind of what the parallel axis theorem does. Okay, as we talked about, for a general region, we have the ability to calculate Ix naught and Iy naught, which are the moments of inertia of a region, Ix naught, Iy naught, the moment of inertia of a region relative to its own centroidal axis. So what I've done is I've taken our rectangle and I've drawn in his own self-centroids. Okay, here's his what we call the X naught axis, that's his self-centroid, and then here's the Y naught axis, his self-centroid. And then what we find is that if I need to find a new combined axis, and often this is due to centroidal calculations, and as we showed with the T-beam, the centroid was at a location that was different than the centroid of this. We have to do something to be able to move this guy down to this line, okay? And that's why we call it the parallel axis theorem. I'm going to take my I calculation based on this axis, and I'm going to move it all the way down to this location, okay? All right, everything else is exactly the same. This may be the centroid of the combined shape, okay? This guy would be your Y centroidal axis, or what we call the new axis. Okay, and all I want to do is be able to take my Ix and Iy calculations for this little area and move them to this new set of axes, okay, which would be your combined behavior. Okay, everything else is exactly the same that we had happening here. All right, the relationship between all of this then is as follows. Okay, the moment of inertia Ix using the parallel axis theorem is the Ix naught guy, so this is his self I value, plus the area of the region that you're talking about multiplied by this distance dy squared. All right. So in our case, we're going to define dy then on this as being the distance in the y direction from here to here. That's dy. Okay. So now if you're above the axis that you're going to, it's a positive value. If you're below the axis you're going to, it's a negative. It's not a big issue. But it turns out that this guy is basically your y naught I minus y bar. Okay. And then this one, the horizontal, is your dx. Okay. And now I see that I had them already drawn, but that's all right. Okay. And similarly, dx is going to be your your x naught I minus your x bar value, and that will get you those. Okay, so that's how you kind of calculate this. So literally it's the perpendicular distance between the distance that you have to move this axis to this one, and these axes have to be parallel to each other as we start to line it. So that's the way we're going to kind of set this up. Okay, so the Ix naught and Iy naught, the Ix naught is the moment of inertia of the area that I'm looking at about his own self centroid x-axis, and the Iy naught is the moment of inertia about his own self centroid y-axis, and then dx then would be the distance, the horizontal distance that we had happening from here to here. Okay, all right, and so those are our perpendicular distances. All right, now you're starting to see that a lot of these calculations become a little redundant. It's really handy to build a spreadsheet to help you with these calculations, because you do them several times and then it just becomes the same thing over and over, and it's just a lot of redundant calculations that you want to do. So that's one of the tools that I have in my pocket is a centroid spreadsheet to help me out with all of this, and even moments of inertia for combined shapes. All right, so as we said, the distance from in the x direction between the two vertical axes, this is the one for these two guys coming up with that distance. Okay, and then this is the one from these two guys coming up with that distance. It's just the coordinate, the x coordinate of the region I'm looking at minus the combined centroid and then it's the y coordinate of the region minus the y centroid. So no major deals there. Okay, all right, so let's go back and we'll revisit our example for our piece here. Okay, so I've redrawn the shape a little bit. This is down here where you guys can see it. All right, so again, just kind of recapping, this is the same shape that we saw before. Okay, and we found that for this region, we found the centroid last time, this C point, if you will, as being some x bar value. So that was x bar, okay, of 3 inches measured from that origin to y bar of 3.38 inches measured up from x. And that locates this point. From there, I've got everything that I needed to do. So what we're going to do is we're going to take our region. I'm going to split it into 2 rectangular regions like we did before. I'm going to call the top as region 1. I'm going to call the web as region 2. Okay, and then everything that I'm going to do, we're just going to go region by region. All right, so for region 1 on here, here are the axes that we're looking at. Okay, so I'm going to draw everything in here. So here's the x naught. That's my self-centroidal axis acting there. Okay, it's horizontal through here. And then my self y naught is acting through that point as well. And that's this dashed line. Now, the way this shape was laid out, okay, the centroid of this guy we said was 3 inches because it was 3 inches from here to get me to the centroid of this guy. And then we know that it was 3 inches from my reference. If I lay in all of my reference, here's my x, and then this guy would be my y. I know lots of x's and y's running around, and that was my origin. That was 0, 0. That I know that the centroid here was 3 inches over from this point, but C1 is also 3 inches over from that point. So they're the same. They're basically the same axis. They have the same location. So that'll be handy for us. And then we know that our x bar, looking on this, then is going to be then the y bar on here would be then the distance from here to here. Again, that's my centroidal x-axis, that's y bar on here, and that the total distance from up here all the way down is my y1 coordinate. All right, so if we calculate our quantities, x minus x bar is 0 inches, y minus y bar is 5.5 minus 3.38, that's a positive 2.12 inches. Okay, so that tells you that because it's a positive value, your region is above the axis. And with that, now I can go in and I can start calculating the contribution of this guy to the total. Okay, and so this is the Ix from region 1 taken about this new centroidal axis. Okay, so the first term that we have was that Ix naught. Okay, and that was, so for a rectangle, we said that was 1/12 the base times the height cubed. So B1 was 6 inches, H1 is 3 inches, we're going to cube that thing, and then plus A1, 3 times 6, times the distance that I'm having to move through this y1 minus y bar value, or 2.12 inches. All right, and so if I plug in all of the math, plug in all my values, you can see them here. Okay, the first term ends up being 13.5 inches to the 4th. Okay, and then the AD squared term, which is the parallel axis point of this, is 80.9. Okay, so you can see that this parallel axis can kick up a huge increase in the moment of inertia over just a basic rectangle by himself. Okay, and that's one of the reasons that you'll see, in construction, that a lot of beams, the old classic I-beam, why they're so commonly used in construction is because they have a monstrous I value because the centroid of this shape is located here. But I'm picking up a huge value of my dy for the flanges. The flanges are contributing a ton to that moment of inertia. So that's evident as opposed to this, as we start to look at that one. So if I do the math on that, that's 94.4 inches to the 4th. Okay, I1, same game, except now we're going about the y-axis. Okay, and so what happens is that, again, you've got to be very careful on our rectangle that we said B was the horizontal and H was the height, but now I'm going relative to this axis. Okay, but B is still the horizontal. So you can see that the H and the V's switch places. So it's 1/12 H1 B1 cubed plus A1 dx1 quantity squared. And so I can plug in, do all the math. Notice that I get a 0 here because it was the same axis. And so that centroidal amount was 54, and then the parallel axis contributed nothing because the axes were the same. And so the total was 54 inches to the 4th. So that's the contribution of the top part of this beam. And then all we do is we go and we repeat the process for the second region. Okay, so it's very, very easy, very, very straightforward. So same game. Okay, here was my C. Okay, and I've gone in and I've drawn all my coordinates. Now I don't have X and Y shown on this picture, but you know it's out here somewhere. Okay, but I do know that from this location, here was my X, that it's 3.38 inches up to the X centroid. Okay, and then it was, I'll go ahead, I'll put it in here. Lay this guy in, this is my Y. And then from here to here was my 3 inches to the centroid of that guy, right? And then this point here is my C2. So C is for the combined, and then C2 is the centroid of the region that I'm looking at, this particular shaded region. All right, and so his centroid location, we know, is 3 inches over, and it's 2 inches up. Okay, and so then what I need is this dy distance, which is the distance between this axis and this axis. So all I'm going to do is I'm going to take 3.38 inches, and I'm going to subtract off 2 inches for us to be able to get that. Okay, and so when I do that, because this point is lower, remember it's going to be y2 minus y bar is the calculation that I do. Well, because it's lower, it is now a negative value, so it's minus 1.38. That gets us there. And then, like we had in the last one, x2 is the same as x bar. That's why that value is a 0. Right? And so then I can go through and I can play the exact same game calculating IX and IY and their contributions. So if I do all the math, plug in all my terms, I get 25.9 inches to the fourth for IX. And then if I do IY, I can come in and I can do get a figure of 2.7 inches to the fourth as a contribution of that guy about the y-axis. So not much at all. All right, so then now that I've got all these contributions taken about the same centroidal axis now, I can come in and I can total them up. All right, and so the combined, again, that's combined. And this guy is also combined. For the composite shape, I can come in and I can just add the two terms that we got together. So this was for region 1 and this was for region 2 for both calculations. So 94.4 plus 25.9 gets me 120.3, and then 54 plus 2.7 gets us 56.7. And so my math comes up. And so these become the section properties for the combined shape of our T-beam relative to its centroidal, its own bending axis. And from this, then you could go on and do your calculations for stresses and strains and deflections and what have you at this point. But this becomes a critical value, the second moment of area. And so the Parallel.Axis theorem is very useful for that. Okay, now let's go back and let's revisit one thing. And I don't have this written up, but we'll do it real quick. Okay, if we go back and we look at the region that we just did with that simple rectangle in the last video, right? If I come by and I do this, okay, this was my x combined axis for what we were saying, but we also said that it was also the centroid of our region that we were looking at. So x combined and x naught. So if I do x naught minus x combined, okay, that's going to end up being a 0 value. Well, by definition, remember that we said that that was dy quantity squared, right? And based on the pictures that we drew before. So now if I write Ix as being Ix naught plus a and then dy quantity squared for us there, I know that this first term, again, this is b wide, this is h tall, okay, and relative to that centroidal point, this was 1/12 of b times h quantity cubed plus then b times h times, well, we just found out that's the same axis. This guy becomes 0 squared, right? And so if I do the math, this becomes 1/12 bh cubed. So we're back to basically having our simple formula that we had in the original example, because for this particular shape, the centroid for this shape by himself was the combined shape. So this is probably a better use of our formula, is to use the Parallel.Axis theorem under all circumstances. And again, you can plug this into a spreadsheet and it becomes fairly easy for us. All right. Okay, now a couple of shapes that might be of use for you. Okay, rectangles are very important. Okay, in fact, let me write these down and we'll go over these and I'll come right back. All right, sorry about that. Rather than you watching me draw, I would just have it and we could go through it a little bit faster. All right, so to recap, let's talk about some of the common shapes that you come up with in basic structural engineering applications. So if we go back and we look at our basic rectangle here, okay, b wide, h high, we already said ix was 1/12 bh cubed, iy 1/12 hb cubed. The b's and the h's flip. All right. Now, there are occasions when doing calculations that it becomes convenient to take my centroid about a different location. And so I'll show you the rectangle that's taken about his base. If you apply parallel-axis theorem with a dimension of dy here, the ADY squared term changes that 1/12 BH cubed term to 1/3 BH cubed. Okay, and like I say, there are reasons to do this. We won't discuss them here, but what you can do with this in parallel-axis theorem, this is a convenient one to have memorized also. The other shape that we have is a regular triangle that's b wide and h tall. Okay, and for that, ix is 1/36, 1/36 BH cubed. Gets us there. Okay, and again, that's assuming that I'm taking a value about his centroidal axis that we know that this distance here is h/3 up from that. Okay, and then you can do similar things in the y direction. The other one that we have then is a circular shape, okay, that has some radius of r, okay, and so ix and iy are the same value in this case. And again, the centroid is located at the center of the circle, and that's pi/4 times r to the fourth, and then iy is pi/4 times r to the fourth, and then j, we said, was ix plus iy, the polar moment of inertia of the circular shape. It becomes pi/2 r to the fourth. And this is an important one in mechanics because in a typical undergraduate mechanics class, you restrain your study of torsion to mostly circular shapes. So you'll be seeing this over and over and over when you get to mechanics and materials. All right. Now, there are other resources for shapes that are irregular. Okay, and so I'll show you a case, that maybe this is a table out of a textbook that I have, but you could be pulling these out of any design manual, AISC, steel construction manual, or what have you, that a lot of times they will call things as a different beam. So what I have here is I have a W8 by 31. Okay, I have an area that is 9.12 inches squared. I'm looking at the one that's here on the bottom. Okay, I have a depth that is 8.0 inches, and again, I know it's hard to see, but that's what these headers are. So this is my depth, okay, and this is my A associated with that, and then my IX for this guy is 110 inches to the fourth, and my IY is 37.1 inches to the fourth. I can read these, and they have all of these tallied up for you because the manufacturers of these shapes conform to a standard that they've all agreed upon, all right, that they'll be within a certain amount of tolerance of, any W8 by 31 that a manufacturer makes will have these section properties within a certain degree of tolerance. Okay, and so what happens is that I can get shapes that are highly irregular. This I-beam actually has rounded edges and it has little rounded fillets in this thing. But as long as I know A, as long as I know IX, and as long as I know IY, if I take a shape that is, something, fairly irregular, it'll look something kind of like, here's my I-beam, and then maybe I come in and I put a plate over the top of him on this. It has some dimensions on it. Then I can go in and I can play the exact same game because I know that if I call this as region 1, I know that IX, for region 1 is going to be equal to I naught for number 1 plus A1 and then dy quantity squared. So all I have to do is come in and on this combined shape figure out what's that C coordinate, and if this is my y bar dimension and then this is my C1 coordinate for the centroid of the I-beam, which happens to be in the middle, I can go play the same game. And so the size of the shape doesn't really matter. Okay, but you got to kind of watch, where they're calling their centroids and the references that they have happening on this. So that's, easily handled and all done by the same thing. This guy, if I called him as region 2, then is IX for number 2 is I naught for 2 plus A2 times dy quantity squared. And that's for dy1, and this is dy2, because clearly his C2 is up here, right? And so then the dy2 would be that dimension and so forth. And then all I do is I sum these guys to whatever that value needs to be. So that's one of the things that we can do. Pitfalls that can happen, especially in the AISC shapes. If the shapes are irregular, you got to kind of look at where they're calling their origin. So in the case of this example that we had, you can see that they always call out y and x dimensions. So the centroid is the coordinate, the location of the centroid is where those 2 points cross. Okay, now, for shapes that are a little bit irregular, like say maybe this channel on the back, it's the same kind of game. The centroid is here at that crossing point. Okay, but what they do is they spell out x bar as being from the back of this flange, or the back of the web, over to that centroidal axis. So if I draw this up a little bit bigger so that you can see it, it'll look something kind of like that, that the centroid is located here, and they set the axes such that this dimension is x bar. Well, this can be, you've got to be very, very careful on what they call these dimensions, because, if I put this on top of an I-beam on here and I orient the piece this way, okay, it's very different than the same I-beam, same sections, with a piece that is oriented where I turn it the other direction. It looks something kind of like that. Okay, and part of that has to do with, in this one, that centroid, if this is region 2, the centroid that is here was way up there, and then my combined axis is down here, versus now the centroid of that same region is now down here somewhere for region 2, and my combined axis is, at some other location. Even your y bars are different for this. This is, y bar A, and this is y bar B. Okay, so you got to kind of watch how they're defining these. So, in the table, they, in that particular case, they said x bar for this small guy would be depth, width. It's here somewhere. Okay. Well, wherever it is, I'm not seeing it now. Axis y. Oh, there it is. It's this value. This 0.812 or 0.512 inches. So this is 0.512 inches. All right. And so you can see that that makes a difference on that parallel distance. And so you've got to kind of watch the orientations on this. And, and the other part that makes this confusing is that what is relative to this axis, that horizontal axis, the IX02 on this guy is actually the IY of that shape as it's recorded. All right. Again, because you've turned the axis and you've watched the orientation. So there's some tricks that can happen. And again, that's kind of getting beyond the scope of what we're trying to do here, but at least want to kind of mention some differences with these orientations that you want to kind of watch on those. But otherwise, everything else is parallel axis theorem, and it comes back to these formulas. And you can just break this thing up and, and have at it. So anyway, I know we kind of went off on a little bit of a tangent there, but this is important in structural design, especially in a steel class. So if you're one of my steel students coming by to look at this video, we've talked about this, and this is kind of a rehash of that. So, but it's useful information to have nonetheless. So anyway, that's all we have for that for today. I know it got a little bit long, but again, it's very, very important to be able to understand how to do these section property calculations, and in particular, the second moment of areas, or the engineering moment of inertia. So anyway, without further ado, as always, if we've helped you out, toss us a comment. Let us know, what you liked, what you didn't like, what we can do differently. Please be sure to like the video if you did, and as always, subscribe to the channel. We do appreciate it. So have a great and wonderful evening, and we will see you next time. Happy engineering.